Welcome back. Hope you had a wonderful holiday season if you're watching this soon after it was uploaded. When I left off, I gave the problem to prove whether or not there are infinitely many primes. In the short time between this video and the last, I have had 0 proof submitted, but a good feel for some of the grievances, and hopefully by the end of the series, these problems will start to go away. I took that problem in particular because it is one everyone can do, but might not know how it is done, and it gives a good intro into proof by contradiction. I'm going to jump right into the proof and then go back and highlight some of the key points of a proof by contradiction. The first thing you would want to do in this scenario would be to assume that there aren't infinitely many primes, and that arithmetic behaves the way we expect to do. Adding behaves properly and multiplying behaves properly. If we have a finite number of primes, we could take all of them and put them into a nice list and package them all together. So we'll take 2, we'll take 53, we'll take 11, we'll put them in a nice list. They're all together, every single prime. Because there's finitely many, we could do that. The next things we'll need are some kind of half theorems, known as lemmas, in order to give us the knowledge we need to prove this. So these are going to be something we're going to prove along the way. They're smaller than the main proof, but we still need them to come with the final proof. This next step should help us with not knowing where to start, as so many people struggled with. Fooling around with the primes, it should be obvious that all composite numbers are not prime. 2 times 3, or 6, is by definition divisible by 2 and 3. So if it's a composite, it is not prime, and if it's prime, it is not a composite. Got that out of the way. Also, with some more experimenting, it should take notice that if we have a number such as 21 that is a multiple of 3 and 7, the next multiple of 3 is 3 away at 24, and the next multiple of 7 is 7 away at 28. Jumping up by any other amount, such as up by 2 to get to 23, will yield a number that is not a multiple of 3 or 7, and is in fact actually a prime number. Pay close attention that this applied to both the 3 and 7 when using this idea of counting by multiples. This isn't a very rigorous lemma, but I'm not trying to prove this for math majors. So in total, that last lemma that we just passed over is that if we have a number composed of certain primes, then its product, the next time that it's a multiple of any of those primes is composed of, will be adding that prime specifically. So that's the abstract version of it. So this last step will be the proof by contradiction. If we took every prime in the list we compiled earlier and multiplied them out, so 2 times 3 times 5 times 7 times 11, etc., we would end up with a number that is a multiple of every prime. So to make a contradiction, all we need is a new prime number to contradict the first assumption we made about there being finitely many primes. So if there's finite, we can make a list, and that list should end. But if we make a new prime at the end of the list, then the list didn't end. So that's a contradiction. So to make this new prime, a number that isn't a multiple of any other prime, we add a number that isn't a prime or a multiple of any other prime. And that number is 1. It's not a multiple of 2, 3, 5, 7. 1's just 1. And if the primes had an end, adding 1 to the product of all primes would result in a new prime. And this contradicts the statement that we can obtain the last prime, leaving us with only one assumption left. There are infinitely many primes. This is actually a pretty close match to Euclid's original proof way back in 300 BC. So to take away from that proof would be how to use the logic of proof by contradiction and how to build up to a proof and get yourself in the right mindset, because proving things really is a creative endeavor. The logic of the proof by contradiction is to assume the opposite of what you are trying to prove and assume nothing else, because when a contradiction is arrived, something must have went wrong somewhere, and if you didn't make a mistake in calculation or messed up your algebra, then the only place a falsehood may have arisen is from the assumption that you made. Proof by contradiction is usually one of the places I go when I'm trying to prove a true or false statement and a direct method is eluding me. In the prime example, a proof of their infinitude would have been directly finding a formula for primes and knowing that there are no restrictions. But such a formula doesn't exist to my knowledge, so I'm naturally inclined to try a proof by contradiction. Very important though, when starting a proof, because it is a very cumbersome task, is to fool around with what you can get from the definition of the structures at hand, such as what makes a number prime and how can I test if a number is prime. Asking yourself what you can and cannot do boils down to you can use something that is logical, as long as it makes sense, you can always do it, and if you make any other assumptions, you'll have to prove them as separate lemmas. So as an assignment, to get you thinking about the next lesson, which will be geometric proofs, I want you to look at how can you show that the Pythagorean theorem is correct, and if that's not enough for you, using the definition of the area as an equivalent area of a rectangle, so the rectangle is width times height, that's your definition. Try to prove the formula for some additional shapes, like the triangle, or maybe even the circle if you really want to go at it. And as an actual assignment relating to proof by contradiction, I want you to prove that you can't know everything using your proof by contradiction. It isn't what we'd say is math and is more philosophical, but a good exercise nonetheless in terms of proof by contradiction. Submissions will work the same as they did last time, just check the description. And I hope to see you soon, and as always, keep learning.